Chapter 5, Section 7, Differential Equations, Separation of Variables. A lot of repetition in what we're going to talk about in this section, but we are going to dive a little bit deeper into the idea of what's the difference between a general solution and a particular solution. Now, this section is actually, if you look in the book, contains some information on a different type of differential equations that are not easily separated, the ability to separate the variables. Homogeneous differential equations, and that's not part of your AP test, so we're not going to cover any of that. But instead, we're going to talk a little bit about the solution and also how to classify them by order. So, a function y equals f of x is called a solution of the differential equation if the equation is satisfied when y, whatever y is, and its derivatives, we place f of x and its derivatives. So in the example that I have here, it says this is a solution of the differential equation y equals e to the negative 2x. This is a solution of the differential equation y prime plus 2y equals 0. If I find y prime, I get e to the negative 2x times negative 2, chain rule, which is negative 2 e to the negative 2x. If I plug in, I have negative 2 e to the negative 2x plus 2 times y, which is e to the negative 2x is equal to 0. As you can see, it does satisfy the equation. This is a solution. As it turns out, for this particular differential equation, any function of the form y equals c, where c is a constant, e to the negative 2x, is a solution to that equation, and because of that, we refer to it, since c can be any number, as a general solution. I also wanted to make mention, whereas this is a particular solution, I also wanted to make mention that the order of a differential equation is equal to the highest order derivative that's in the equation itself. So here it has y prime, so this is a first order differential equation. F double prime of t equals negative 32, having to do with a free falling object and gravity. This is a second order differential equation. So in the example that I have next, it says determine whether the given function is a solution to the differential equation y double prime minus y equals 0. Another second order differential equation here. I have first off the possible answer y equals the cosine of x, so I need the first two derivatives. The derivative of cosine of x is negative sine x, and the derivative of that would be negative cosine x. And so I'm going to plug this in for y double prime and this in for y. And I get the opposite of the cosine of x minus the cosine of x is equal to 0. I get negative 2 cosine x equals 0. That's false, so no, it is not a solution. In this example, I take the derivative. The derivative of this would be 2e to the opposite of x times negative 1. Again, chain rule. That'd be negative 2e to the opposite of x. And y double prime then would be, well, it just be multiplied by another factor of negative 1 here. So that'd be positive 2e to the opposite of x. So if I plug this in here and this in here, I get 2e to the opposite of x minus 2e to the opposite of x. Yeah, this is going to be a true statement. 0 equals 0. So yes, it satisfies. And this last example, a little bit more of a general idea here, where c is a constant, general solution. I have y prime is equal to, well, the derivative of e to the x, so this would be c e to the x, and the derivative of y double prime would also be c e to the x. So I plug in for the second derivative, c e to the x minus the original, which is c e to the x. Does that equal 0? Absolutely it does. So the first one was not, but the other two are. Now, what happens here is you can see how kind of similar these two guys are, but what happens here is with this, I would have, now we know what the graph of y equals e to the x would be. It's an exponential curve, but with c, depending on if it's positive or negative, you would get a different variation of it. You might get a reflection, or you might get some type of stretching or shrinking of dilation of the graph of y equals e to the x. So in thinking of it in terms of geometry, the general solution of a first order differential equation is a family of curves known as solution curves. And then you get each one of these curves for each value that's defined for the arbitrary constant. So if I plug a 1 in, I get a solution curve. If I plug a 2 in, if I plug a 3 in, and so on down the way. All right. This is coming into play also with something that we're going to study in the next chapter that we've mentioned just barely. That has to do with slope fields, which are kind of a geometric interpretation of the solution of a differential equation. So let's see what else we can do here. Okay. Now, particular solutions of a differential equation, we get those from initial conditions. We've had that in other parts of this book, in other sections, including the last section. And it give values for the dependent variable or one or more of its derivatives for a particular solution to the independent variable. So they give you some information that you can plug in. And that's what these next couple of examples are about. Actually, not so much this one, but this example and the one that follows here after this guy. For the differential equation, x, y prime minus 3y equals 0, first order differential equation, we want to verify that y equals c x to the third is a solution. So I know how to do that. I'm going to plug it and its derivatives in, and then we're going to find a particular solution given these initial conditions. So first things first, I have y equals cx to the third. I'm going to need y prime, which would be 3cx to the second. So I go back to here, x, y prime minus 3y equals 0. Plug these in. So in for y prime, I put in 3cx squared minus, and then in for y, I plug in cx to the third. Let's see. Does that look right? Oh, I forgot the 3. Son of a gun, I forgot the 3. Be careful. And that equals 0. So that's 3cx cubed minus 3cx cubed. Yeah, that 3 is important. So yes, indeed, it is a solution. Now, to find the particular solution, all I'm going to do is substitute these values in, find my value of c, back into this guy right here. So I have y equals cx to the third, so it would give me 2 equals c times negative 3 to the third. 2 equals negative 27c. c is equal to negative 2/27. So that gives me y equals negative 2/27 x to the third. That is my particular solution. All right, now it says here, note, to determine a particular solution, the number of initial conditions must match the number of constants in the general solution. So you have to be careful there. I had one constant in my general solution, and I had enough of the conditions, the initial conditions, to help me out with that. Now it says here in this one, find a general solution of this. Well, it's time to separate those variables. So I get dy over y equals x all over x squared plus 5 dx. I separated the variables. I'm going to integrate both sides. I'm going to come over here. Natural log of the absolute value of y is equal to, now here to integrate this side, I have to kind of juggle the constant a little bit because it's going to be a du over u. So I need a 2 here and a 1/2 out in front. So I get 1/2 the natural log of the absolute value of x squared plus 5, which would just be x squared plus 5 because it's always positive, plus a constant. All right, so now I can rewrite this, if I choose to here, as, let's see, where am I at? As the absolute value of, or natural log of the absolute value of y is equal to the natural log of the square root, raising this up as a power here, of x squared plus 5, all that plus c. If I raise both sides to the e to that, I get the absolute value of y is equal to e to the natural log of the square root of x squared plus 3 plus c. Now that's the same thing as e to the natural log of the square root of x squared plus 3 times e to the c, which is a constant. And so I'm going to drop the absolute value, and I'm going to put the plus or minus in this constant, and I'm going to write this as y equals c sub 1. Of course, e to the natural log of that is just going to be the square root of x squared plus 3. Is that a 3 or a 5? It's a 5. I can't even read my own writing here. It's a 5. Somewhere along the line it changed from a 5 to a 3. Now it's back. Okay, there's my guy right here. Have to be a little dance around a little bit there with the algebra. Alright, the last guy, given the initial condition y of 0 is equal to 1, find the particular solution given x, y, dx is equal or plus e to the opposite of x squared times the quantity y squared minus 1 dy. I'm going to separate the variables, but first I'm going to separate these two terms here. Let's see, the opposite of e, the opposite of x squared times y minus 1 dy. I'm going to have to divide both sides by y and divide both sides by the opposite of e to the opposite of x squared. Yikes! So if I divide both sides by y and by the opposite of e to the opposite of x squared, oops. Why do I do this to myself? I love this algebra. So the y's cancel, and I have, I'm going to pop him up top. I'm going to write him as negative e to the x squared, because now he goes from the denominator to the numerator. The exponent changes sign. Dx, whoops, x dx, put the x in front. And then on this side, let's see, what did I cancel this with this? And I have y minus 1 over y, which would be 1 minus 1 over y dy. I'm going to raise both sides here. And let's see, I have to put the negative out in front and put a 2 in here, so this is going to be a negative a half. Over here, I think I can integrate that. This is going to be negative 1/2 e to the x squared plus a constant is equal to y minus the natural log of the absolute value of y. Now here's an example of a problem where it is not convenient to solve for y. You can see the y is here, and then the y is in the inside the natural log here. So in this case, that's about as far as I would take it. Now, if I wanted the general solution, I'm done. But I want the particular solution, given y of 0 is equal to 1. So when x is 0, y is 1. So when x is 0, y is 1. Well, the natural log of 1, of course, is 0. All this is just negative 1/2 times 1. So I have negative 1/2 plus c is equal to 1. So that gives me c is equal to 3/2. Here we go. I'll go ahead and put this on this side first. I'm going to write y minus the natural log of the absolute value of y is equal to negative 1/2 e to the x squared plus 3/2. I might multiply through by 2 just to neaten it up a little bit. If I multiply through by 2, I get the opposite of e to the x squared plus 3. And then I can bring the exponent up here, so that's y to the second power, absolute value of y to the second power is just y squared. So I can write y minus the natural log of y squared is equal, with the 3 minus e to the x squared. That is a mess, but that would be as good as I can get for my particular solution. The good news is you don't encounter this very often. Most of the time it works out a little bit more like the other problems, a little bit more nicely, but it's good practice all the same. If you can do the tough ones, you can do the easier ones just that much more quickly. All right, so practice, practice, practice.